Imagine a universe where stars aren't just distant suns, but cosmic engines whispering secrets across unimaginable gulfs. A universe where the very fabric of reality can twist and warp, where shadows hold more substance than light, and where the building blocks of everything we know behave in ways that defy our deepest intuitions. This isn't science fiction. This is the universe we are discovering. This is the universe that gets stranger and more profound the deeper we look. For millennia, humanity gazed at the night sky, seeing a celestial dome, a predictable clockwork of wandering stars and fixed constellations. We mapped their paths, named their patterns, and built myths around their distant glow. It was a universe of elegant simplicity, a grand, well-ordered stage for our terrestrial dramas. But as our eyes sharpened, as our tools grew more powerful, that simple picture began to fracture. The deeper we peered, the more the familiar dissolved, replaced by phenomena that challenged our very understanding of existence. We started with the visible. Telescopes revealed nebulae, vast clouds of gas and dust, the birthplaces of stars. We saw galaxies, island universes far beyond our own Milky Way, each containing billions of suns. This was already awe-inspiring, a testament to the sheer scale of the cosmos. But then, we began to probe beyond the visible spectrum. We learned to listen to the universe, to hear the faint whispers of radio waves, the energetic cries of X-rays and gamma rays. And what we heard was astonishing. We discovered pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses, sweeping across space with unfathomable precision. We found quasars, impossibly bright and distant objects powered by supermassive black holes at the centers of galaxies, outshining their entire stellar populations. These weren't just distant lights. They were engines of immense power, operating under physical laws that pushed the boundaries of our knowledge. But the true strangeness began to emerge when we looked at the invisible forces that govern the cosmos. We saw that galaxies didn't spin as they should, that their outer regions moved too fast, as if held together by an unseen hand. This led to the concept of dark matter, a mysterious substance that makes up the vast majority of the universe's mass but doesn't interact with light, remaining stubbornly hidden from our direct observation. It's like trying to understand a room by only looking at the furniture, unaware of the walls and the air that hold it all together. Then came dark energy. We observed that the universe isn't just expanding, it's expanding at an accelerating rate. Something is pushing galaxies apart, overcoming gravity's relentless pull. This dark energy, even more enigmatic than dark matter, is thought to constitute the largest portion of the universe's total energy density. It's a force so fundamental, so pervasive, that it dictates the ultimate fate of the cosmos, yet we have only the faintest inkling of its true nature. Our understanding of space itself has also been revolutionized. Einstein's theory of relativity revealed that space and time are not separate, immutable entities, but are interwoven into a single fabric, space-time, which can be warped and curved by mass and energy. This led to the mind-bending concept of black holes, regions where gravity is so intense that nothing, not even light, can escape. They are cosmic drains, points of no return, and their interiors remain one of the universe's greatest mysteries. And the quantum realm, the subatomic world that forms the foundation of all matter, is a place of bewildering paradoxes. Particles can exist in multiple places at once, can be entangled such that they instantly influence each other across vast distances, and their very observation can change their behavior. The universe at its smallest scales operates by rules that seem to defy logic, yet these rules are the bedrock of the grand cosmic structures we observe. The deeper we look, the more we realize that our everyday intuition, honed by our experience on a single planet orbiting a single star, is insufficient to grasp the true nature of reality. The universe is not just vast, it is profoundly weird. It is a realm of unseen forces, of exotic matter and energy, of warped space-time, and of quantum strangeness. And the more we uncover, the more questions we have, each answer leading us to even deeper, more astonishing mysteries. Join us as we delve into the extraordinary, the perplexing, and the breathtakingly beautiful strangeness that lies at the heart of our universe. Placed by phenomena so bizarre, so counterintuitive, that they force us to fundamentally rethink our place in the cosmos and the very nature of existence. Today, we're embarking on a journey into that strangeness, a journey that starts with the light from distant galaxies and ends in the quantum foam of spacetime itself. We'll explore why the universe, when examined closely, reveals itself to be far more peculiar and infinitely more fascinating than we ever dared to imagine. Our first step into this cosmic strangeness begins with light. For centuries, we thought of light as a simple wave, like ripples on a pond, or a stream of tiny particles, like bullets. But as we studied light from the most distant corners of the universe, we found it behaving in ways that couldn't be explained by either of those simple models. The light from a star, for example, isn't just a single color. It's a spectrum, a rainbow of different wavelengths, each telling a story about the star's temperature, composition, and even its motion. When we look at light from faraway galaxies, these spectral lines are shifted. They're shifted towards the red end of the spectrum. This phenomenon, known as redshift, is the cosmic equivalent of a siren's wail as an ambulance speeds away. It tells us that the universe isn't static, it's expanding. And not only is it expanding, but the further away an object is, the faster it's receding from us. This is the foundational observation that led to the Big Bang theory, the idea that our universe began in an incredibly hot, dense state and has been growing ever since. But the strangeness doesn't stop at expansion. As we look deeper, further back in time, we encounter light that has traveled for billions of years. This ancient light carries information about the universe when it was just a fraction of its current age. And what it reveals is a universe that was remarkably uniform, almost eerily so. The cosmic microwave background radiation, often called the afterglow of the Big Bang, is a near-perfect blackbody spectrum, meaning it's incredibly smooth and consistent in all directions. This uniformity, however, presents a puzzle, the horizon problem. If the universe began expanding uniformly from a single point, then regions of the universe that are now widely separated would never have had time to communicate with each other, to equalize their temperatures. Yet, they are almost exactly the same temperature. How could this be? This is where things get truly weird, and we introduce the concept of inflation. The prevailing theory suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, a period of hypergrowth that stretched it to unimaginable sizes almost instantaneously. Imagine a tiny, smooth patch of space-time suddenly inflating like a balloon, stretching it so thin that points that were once incredibly close together are now separated by vast distances, yet they retain the memory of their initial thermal equilibrium. Inflation elegantly solves the horizon problem, but it also introduces its own set of strangeness. It suggests that the universe we see is just a tiny bubble in a much larger, perhaps eternally inflating, multiverse. Our observable universe is like a single dewdrop on an infinitely expanding cosmic ocean. Beyond the grand scale of expansion and inflation, the deeper we look into the universe, the more we encounter the profound mysteries of its fundamental constituents. We're not just talking about stars and galaxies anymore. We're talking about the very particles that make up everything. At the subatomic level, the rules of classical physics, the rules that govern our everyday experience, break down completely. This is the realm of quantum mechanics, and it's where the universe gets truly mind-bending. Consider the electron, a fundamental building block of atoms. In classical physics, an electron would be like a tiny planet orbiting a nucleus. But in quantum mechanics, an electron doesn't have a definite position or momentum. Instead, it exists as a probability cloud, a fuzzy wave of potential locations. It's only when we try to measure its position that it collapses into a specific point. This is the famous wave-particle duality, where entities can behave as both waves and particles depending on how we observe them. It's as if a coin could be both heads and tails simultaneously until you look at it, at which point it decides to be one or the other. This probabilistic nature extends to other quantum phenomena. Take entanglement. Two particles can become entangled, meaning their fates are linked, no matter how far apart they are. If you measure a property of one entangled particle, say its spin, you instantly know the corresponding property of the other, even if it's on the other side of the galaxy. Einstein famously called this spooky action at a distance, because it seems to imply faster than light communication, which violates another fundamental principle of physics. Yet, experiments have repeatedly confirmed that entanglement is real. It's as if you have two gloves, one left and one right, in separate boxes. You send one box across the universe. The moment you open your box and see a left glove, you instantly know the other box contains a right glove. But in quantum mechanics, it's more profound. The gloves don't left or right until you look. As we delve deeper into the quantum world, we encounter even more perplexing concepts. The uncertainty principle, formulated by Werner Heisenberg, states that there are pairs of properties, like position and momentum, that cannot be known with perfect accuracy simultaneously. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring instruments, it's a fundamental property of nature. It means that at the deepest level, the universe is inherently fuzzy and unpredictable. And then there's the vacuum. We tend to think of empty space as, well, empty. But in quantum field theory, the vacuum is teeming with activity. It's a seething cauldron of virtual particles popping in and out of existence for fleeting moments. These quantum fluctuations have measurable effects, like the Casimir effect, where two uncharged metal plates placed very close together experience a small attractive force due to these vacuum fluctuations. So, even the deepest void is not truly empty, it's alive with transient possibilities. This quantum weirdness isn't confined to the microscopic realm. It has profound implications for the large-scale structure of the universe. The tiny, random fluctuations in the early universe, amplified by inflation, are believed to be the seeds from which all the large-scale structures we see today, galaxies, clusters of galaxies, and the vast cosmic web, eventually grew. So, the very fabric of the cosmos, its grand architecture, is ultimately rooted in the probabilistic, fuzzy, and deeply counterintuitive rules of quantum mechanics. Moving from the subatomic to the cosmic, we encounter another profound strangeness: dark matter and dark energy. When we observe galaxies, we see them rotating much faster than they should based on the visible matter they contain. The stars on the outer edges are moving so rapidly that they should be flung off into space. This suggests that there's a significant amount of invisible, dark matter, providing the extra gravitational pull to hold these galaxies together. We can't see it, we can't directly detect it with our current instruments, but its gravitational influence is undeniable. It makes up about 27% of the universe's total mass-energy content, dwarfing the ordinary matter that forms stars, planets, and us. But the strangeness doesn't end there. Even with dark matter, the universe's expansion isn't behaving as expected. Observations of distant supernovae reveal that the expansion of the universe isn't slowing down due to gravity, as we might expect, it's actually accelerating. This acceleration is attributed to dark energy, a mysterious force that seems to be inherent to space itself, pushing galaxies further apart. Dark energy is estimated to constitute about 68% of the universe's total mass-energy content, making it the dominant component of our cosmos. The implications of dark matter and dark energy are staggering. They mean that everything we can see and interact with, all the stars, planets, nebulae, and even ourselves, constitutes only about 5% of the universe. The vast majority of the cosmos is made of stuff we don't understand, stuff that doesn't interact with light in the way normal matter does. We are essentially living in a universe dominated by invisible, enigmatic components. This is a profound, humbling realization. We've spent millennia studying the visible universe, believing it to be the whole story, only to discover that it's merely a tiny fraction of a much larger, stranger reality. The quest to understand dark matter and dark energy is one of the most pressing challenges in modern physics and cosmology. Are they new fundamental particles? Are they modifications to Einstein's theory of gravity? Or is there something even more exotic at play? The answers to these questions will undoubtedly lead us to even deeper levels of cosmic strangeness. As we continue to refine our telescopes and our theoretical models, we push the boundaries of our knowledge, venturing into realms where our everyday intuition fails us. Consider the bizarre nature of black holes. These are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are formed from the gravitational collapse of massive stars, and at their heart lies a singularity, a point of infinite density and zero volume. Our current laws of physics break down at the singularity, and what happens inside a black hole remains one of the universe's greatest enigmas. The event horizon of a black hole, the boundary beyond which escape is impossible, is another fascinating aspect. If you were to cross it, you would be stretched and squeezed by tidal forces in a process aptly named spaghettification. But what happens on the other side? Does it lead to another universe? Does it lead to a region of spacetime where time and space are reversed? These are questions that push the limits of our imagination and our understanding. Furthermore, the study of black holes has led to the information paradox. According to quantum mechanics, information cannot be destroyed. However, if something falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what happens to the information it contained? Does it disappear forever? This paradox highlights a fundamental tension between general relativity and quantum mechanics, suggesting that a more complete theory of quantum gravity is needed to reconcile these seemingly conflicting principles. The universe also presents us with phenomena that challenge our very understanding of space and time. Wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe or even different universes, are a theoretical possibility arising from Einstein's field equations. While purely speculative at this point, their existence would revolutionize our understanding of cosmic connectivity and the potential for interstellar travel. Then there are the exotic states of matter that exist under extreme cosmic conditions. Neutron stars, for instance, are incredibly dense remnants of supernovae, packing more mass than our Sun into a sphere only about 20 kilometers in diameter. They are essentially giant atomic nuclei, with electrons and protons crushed together to form neutrons. The pressures and densities within a neutron star are so extreme that they push the boundaries of our understanding of nuclear physics. And at the very edge of our observable universe, we encounter quasars, incredibly luminous active galactic nuclei powered by supermassive black holes at their centers. These objects are so bright that they can outshine entire galaxies, and their intense radiation can influence the evolution of their host galaxies. Studying quasars allows us to probe the early universe and the formation of the first supermassive black holes. The more we study the universe, the more we realize that our familiar concepts of space, time, matter, and energy are just approximations, useful for our everyday experience but insufficient to describe the full reality of the cosmos. The deeper we look, the more we encounter phenomena that are not only strange but also fundamentally challenge our deepest intuitions. This strangeness isn't a sign of our ignorance, it's a testament to the universe's incredible richness and complexity. The very act of observation in the quantum realm also introduces an element of strangeness. The observer effect suggests that the act of measuring a quantum system can alter its state. This raises profound philosophical questions about the nature of reality and our role as observers. Is the universe only fully realized when it is observed? This is a question that blurs the lines between physics and philosophy, reminding us that our pursuit of cosmic knowledge is also a journey of self-discovery. Consider the possibility of parallel universes, or the multiverse. While speculative, various theoretical frameworks, such as string theory and eternal inflation, suggest that our universe might be just one among many. Each universe could have different physical constants, different laws of physics, and different histories. This idea, if true, would mean that the universe we inhabit, with its specific set of laws and conditions that allow for life, might not be unique but rather one of countless possibilities. The implications for our understanding of existence are profound, suggesting that our universe's apparent fine-tuning for life might simply be a statistical inevitability in a vast cosmic landscape. The deeper we look, the more we are confronted with the fact that our universe is not only vast and ancient but also incredibly dynamic and evolving. We see evidence of cosmic evolution, from the formation of the first stars and galaxies to the ongoing processes of star birth and death, supernova explosions, and the formation of new planetary systems. This cosmic ballet, played out over billions of years, is a constant reminder of the universe's ceaseless transformation. The quest for a unified theory, a theory of everything, that can reconcile general relativity and quantum mechanics, is driven by the desire to understand these deeper levels of strangeness. Such a theory would hopefully explain phenomena like the singularity within black holes, the nature of dark matter and dark energy, and the very origins of spacetime itself. It's a monumental undertaking, requiring us to push beyond our current paradigms and embrace new ways of thinking about the fundamental nature of reality. Ultimately, the strangeness we encounter as we look deeper into the universe is not a cause for despair or a sign of failure. It is, in fact, the most exciting aspect of our cosmic exploration. It means that the universe is far more wondrous and mysterious than we could have ever imagined. It means that there are still profound discoveries to be made, challenges to be overcome, and new frontiers of knowledge to explore. The universe, in its infinite complexity and profound strangeness, is an unending source of inspiration and a constant invitation to wonder. It is a testament to the power of human curiosity and our insatiable desire to understand our place within this grand, mysterious, and ever-unfolding cosmic tapestry. The journey into the deeper, stranger universe is far from over. It has only just begun. And so, we've journeyed from the familiar dance of planets around stars to the mind-bending realms of quantum entanglement and the vast, unseen forces shaping our cosmos. We've seen how the universe, when scrutinized closely, refuses to conform to our everyday intuitions. From the probabilistic nature of subatomic particles to the mind-boggling scales of cosmic structures, each step deeper into the universe reveals not simpler answers, but more profound and elegant complexities. The universe, it turns out, is not a clockwork mechanism, predictable and easily deciphered. Instead, it's a dynamic, ever-evolving entity, a symphony of forces and phenomena that often defy our most logical assumptions. The very act of observation can influence the outcome, as quantum mechanics so elegantly demonstrates. The vast emptiness between galaxies is not truly empty, but teeming with dark matter and dark energy, the invisible architects of cosmic expansion and structure. And as we gaze further back in time, to the very first moments after the Big Bang, we encounter conditions so extreme, so alien, that our current understanding of physics strains to contain them. This inherent strangeness, this departure from the mundane, is not a bug in the cosmic code, it's a feature. It's the universe's way of telling us that our current models, while remarkably successful, are incomplete. The quest for a unified theory, that elusive theory of everything, is not just an academic pursuit, it's a fundamental human endeavor. It's the drive to connect the infinitesimally small with the unimaginably large, to weave together the threads of quantum mechanics and general relativity into a single, coherent tapestry of reality. Imagine understanding the very fabric of spacetime, the genesis of the universe, the enigmatic nature of black holes, all through one elegant framework. This is the grand prize, the ultimate unification that beckons us forward. The mysteries of dark matter and dark energy, which constitute the overwhelming majority of the universe's mass energy content, remain perhaps the most pressing challenges. What are they? How do they interact? Their influence is undeniable, shaping galaxies and driving cosmic expansion, yet their true nature remains shrouded in darkness. And then there are the black holes, cosmic enigmas where gravity reigns supreme, warping spacetime to such an extreme that even light cannot escape. Within their event horizons lie singularities, points of infinite density where our current laws of physics break down completely. These are not mere theoretical curiosities. They are tangible manifestations of the universe's profound strangeness. But this strangeness is not a sign of futility. It is, in fact, the very engine of discovery. It means that the universe is far richer, far more wondrous, and far more mysterious than we could have ever conceived. It's a constant invitation to question, to explore, to push the boundaries of our knowledge. Every puzzling observation, every seemingly inexplicable phenomenon, is a stepping stone, guiding us towards a deeper and more complete understanding of our cosmic home. The universe is an infinite canvas of possibility, and we are just beginning to sketch its outlines. The journey into the deeper, stranger universe is not a solitary endeavor. It is a collective human undertaking, fueled by curiosity, ingenuity, and a shared desire to comprehend our place within this magnificent, unfolding cosmos. From the painstaking observations of astronomers to the abstract theories of physicists, each contribution adds another brushstroke to our understanding. So, what's next? The universe, in its boundless complexity, continues to pose questions. The search for extraterrestrial life, the exploration of exoplanets, the development of next-generation telescopes capable of peering even further back in time, these are all part of the ongoing quest. The cosmos